right, here we go with our next video. This is section 4.2, graphs of logarithmic functions. We're on page 291 or so of your workbook. Anyway, so let's get moving on this. So this continues on from last section. Last section was graphs of exponential functions. And so we had growth and decay, and we looked at it a little bit from a transformations point of view. In general, this chapter is not so much about the transformations point of view, but that is part of our outcomes of what we expect to be able to do in here. And so we're going to do the same thing with logarithmic functions. So last time we saw this idea of an exponential function is just when we have, like I said, exponential growth or exponential decay, and we had a horizontal asymptote, and the domain was all real numbers. What happens with this kind of ends up being the opposite of what we have for exponential, and in fact, we use the term inverse. So just like when we multiply by something, the inverse operation of multiplying would be to divide something. If you cube something, then the inverse operation to that would be cube rooting. So what we end up with here is a logarithm ends up being the inverse operation of an exponential. All right, so this starts off with our grid where we're graphing y is equal to 10 to the x. We're going to label y-intercepts and horizontal asymptotes, and we see what this looks like, and then we're going to graph the inverse of it. So just starting with the original, y is equal to 10 to the x, we have a domain of all real numbers, and so we have going from negative infinity to infinity. I'll write this one in the interval notation. Our range, like we saw before, is everything from 0 to infinity. We had no x-intercept. We had a y-intercept at 0, 1, because 10 to the 0 is equal to 1, and we have a horizontal asymptote is equal to 0. So this looked like this. We had 0, 1, and it's going to go up very quickly. 10 to the 1 is just 10, and so this gets very steep very quickly. 10 squared is equal to 100, so we can see that it's going to continue upwards and be very, very steep. So the idea of an inverse of this function is it means we are going to swap your x and your y in your equation. And so if we swap our x and our y, we come up with this. X is equal to 10 to the y. When we try to graph that, when y is 0, we have 10 to the 0, so we have x is equal to 1. So at this point, 0, 1, on this new graph, we have 1, 0. And if we look at some other points, when y is 2, when y is 1, x would be 10 to the 1. So when y is 1, x is 10 to the 1. So it's going to go off in this direction. If we plot out some points, you can see that it starts to look like this. It ends up kind of being a smooth curve, but it ends up going very steeply in that direction. What we can see from this is x is equal to 10 to the y. We make x is equal to -1. This will never happen, right? There's no value of y that you can have as an exponent of 10. So it ends up being a negative number. So what we end up with here is we end up with a vertical asymptote on this line, whereas on our exponential, we have a horizontal asymptote. So we end up with our domain goes from 0 to infinity, not including 0 because we have an asymptote there. Our range ends up being real numbers, because this will continue to go up even though it's not going to be very steep at all. In fact, it's very not steep, but it will keep increasing. X-intercept, we have an x-intercept at 1, 0, and we have no y-intercept. For asymptote, we have a vertical asymptote at x. So notice that everything that happened here, our domain became our range and our range became our domain. All of our points, 0, 1, moved to 1, 0 as its image. If we took this inverse as a transformation, that would be the image of that point. And in fact, every single point would be you just swapping the coordinates. And so if we have, up here we have 1, 10, that would correspond to, on this graph, 10, 1. So back when we did inverses in transformations, we recognized that you just swap your x and your y coordinate. You swap your x and your y in your equation, and that ends up being how we do an inverse. The last piece about this that I'm going to mention is just to remind you that this was a reflection. The inverse ends up being a reflection in the line y equals x, and we can kind of see that ends up being true. Okay, so what does this have to do with this word logarithm? The idea is if we create this x equals 10 to the y equation, and we want to solve it for y, it's really kind of hard to do without introducing this new notation. Our new notation is called logarithm, and we write it like this: y is equal to logarithm of x base 10. So this equation here, x equals 10 to the y, means the exact same thing as y is equal to logarithm of x base 10. So we are going to use this as a tool to swap back and forth between this exponential form of this equation, which means the same thing as this logarithm form of the same equation. We'll do that when we want to algebraically solve for something that's in the exponent, or we'll do it if we want to algebraically solve for something that's within the logarithm. For now, let's focus on the graph of logarithms and their transformations. If we know all the key characteristics of an exponential, then we know all of the associated logarithmic characteristics. Okay, so again, just kind of relating this back to transformations for a little bit. The a value, if we have y is equal to a logarithm of b bracket x minus h base 10 plus k. Notice that when we read this, our base number, that tiny little subscript number of 10, that ends up being kind of an afterthought when we read it out. We're actually taking the logarithm of b bracket x minus h, and it just happens to be in base 10. So when we start to fill this in, no surprises that a ends up being a vertical stretch by a factor of a. It's a stretch about the x-axis, of course. How is this going to affect the key characteristics of our logarithmic graph? Remember that our logarithmic graph has a vertical asymptote at 0. If we stretch it vertically, it doesn't affect the x-intercept, doesn't affect the asymptote, and so it doesn't. Those key characteristics. If we have a b value, so b ends up being a horizontal stretch, no surprise, about the y-axis by a factor of 1 over b. If we horizontally stretch it, it stretches the x-intercept. 1 over b is far stretching line is your y-axis. The asymptote doesn't move because the asymptote is on the y-axis. Our h value, horizontal translation. We have a horizontal translation or horizontal shift. This shifts your vertical asymptote and your x-intercept. Shifted left if h is negative, right if h is positive. And a k value is a vertical translation. Okay, is a vertical translation. If we translate this vertically, it doesn't affect your vertical asymptote, of course, but it will affect your x-intercept. Our x-intercept is shifted. All right, so the last part about this, technically it's not a transformation. If we change what the base um, we are using, remember that when we did this with exponential, if we changed our base, a growth function was when we had a b value greater than 1, and a decay function ends up if we had a b value between 0 and 1. So the same thing is going to happen with a logarithm. And in fact, if we just take each of those and we take the inverse of them, we reflect them in the line y equals x, you swap all your coordinates. If b is greater than 1, it will be increasing. It'll look like this. The one that we've just seen. B is between 0 and 1. It still has a vertical asymptote. It is decreasing. So number 1, state the transformations that have occurred. Y is equal to 3 logarithm of 2x plus 4 base 10 plus 6. No real surprise with this. We first need to make that 2. We're going to factor it away from your x, so this becomes 2 bracket x plus 2. This is base 10. And then we've had a vertical stretch. Factor is 3 about the x-axis. Stretch factor 3 about the x-axis, horizontal stretch. Stretch factor is, of course, 1 over 2, because b is 2. Stretching it about the y-axis. We have a vertical translation up by 6. And our last piece is our horizontal translation. We now have a h value that's negative 2, so this is going to the left by 2. Again, as we've talked about before, we list our stretches first, and then stretches and reflections first, and then we would list our translations afterwards. It doesn't really matter the order between vertical and horizontal, which we do first within those, but for sure we have to list our stretches first and then our translations. Our vertical asymptote. So our vertical asymptote is really only going to move if we have had a horizontal translation, and so we've translated to the left by 2, and so we end up with a vertical asymptote that is the line x. Whether this is increasing or decreasing, because it's a logarithmic function that it is base 10. Because if b is greater than 1, we have increasing. In range. So let's maybe start to sketch this a little bit. This looks like it's been stretched vertically by a factor of 6. It's been stretched horizontally by a factor of half. And then once we've done those 2 stretches, now we shift it, everything to the left by 2, and everything up by 6. And so we end up with something that's going to look like this. So for domain and range, our domain being the set of x such that x is greater than -2. Range. The range for logarithmic, unless we have a context, is going to be just like our domain for an exponential was all real numbers. All right, so for number 2, it's kind of the same thing. So maybe hit pause for a minute and see if you can do this all on your own. I'm sure you can. So I'll see you back here in a moment. Okay, so hopefully when we did this, we started with the fact that we have a factor in front of a coefficient in front of our x. And so we have to factor that away from your x. So this ends up being 5 times the logarithm of -1/6 x. Now this part ends up being a little tricky and sometimes throws us off. The gaps, that +7's out there on the end. This base 10 is right there. Okay, so when we common factor out -1/6, because we're common factoring a fraction, sometimes this throws us off that we end up just dividing this by 6, and so you would maybe call that x -2, but be careful. When we're factoring out -1/6, we have to, the negative part shouldn't be a problem, but what ends up being the deal is we are multiplying by 6. And you can kind of see that if you wanted to now go backwards and distribute it back in, then that would end up being +12. So you can see that that makes sense if we look at it that way. So when we're common factoring out 1/6, we have to be multiplying both the x term and the constant by 6. And so that's what we've done here, actually -6 in this case. All right, all of that said, now we have a vertical stretch. Stretch factor in the, so you can either state that this is in the x-axis or in the line y equals 0. Either way, you can, sometimes you see it as either goes. We have a horizontal stretch. We have a stretch factor. We have a 1/6 as a b value, so we have a stretch factor of 6. X equals 0. We also have a horizontal reflection. X equals 0 in the y-axis. We have vertical translation. 7 and horizontal translation. To the right, 72. Determine the equation of the vertical asymptote if it's been shifted to the right by 72. So there is your vertical asymptote. It's x equals 72. Whether this is increasing or decreasing. So now, um, because this is base 10, you would think that it is increasing. So normally we would have something that looks like this. Here's line x equals 72, and this would be like this. But we have had a horizontal reflection as well. So it's no longer going to look like that. It's actually going to be like this. And so, although e is equal to 10 is e is greater than 1, increasing. The reason here, though, is although b is equal to 10 is greater than 1, which would make it increasing, there has been horizontal reflection. So the graph is decreasing. So on your diploma exam, you would make that clear in your explanation about what's going on with this. Okay, and so then the last piece, state the domain and range. So again, if so here's 72, it's been horizontally reflected, and it's going to look, that's horrible, but it's going to look something like as bad. Okay. State our domain and range just by going from that. From negative infinity to 72. Round bracket because it's not equal to 72, and the range is all real. All right. So to determine the equation of our transformed function, so that's the top one, or this is not necessarily the top one, the one that's in red, y is equal to a log x, is this one here. Because the other one is labeled as y is equal to log x. The other one, y equals log x, is just a, if there's no number written there as a base, if we have y is equal to logarithm x, if there's no number written as a base, it's understood to be base 10. Kind of like if you have y is equal to a square root, if there's no number for a root there, that's an invisible little 2. It's just understood to be square root. So with a logarithm, if there's no number written there, it is base 10. And in fact, that's kind of what's going on with this first graph is here we have the point 10, 1. The only thing that we've done to this is we have an a value. So we have stretched this. This appears to be at 10, 5. And so therefore, 10, 1 mapped to 10, 5. So we could do this algebraically. We could say that 5 is equal to a times the logarithm of 10. We can push that into your calculator. A is equal to 5 over logarithm of 10. And you have a log button on your calculator. That is for your common logarithm, so it's in base 10. And so when we do this, you'll find that logarithm of 10 is just 1. And so this ends up being a equals 5. So therefore, y is equal to 5. Sorry, logarithm of x is 5 log x. All right. This next one, we have, it looks like we have a vertical stretch. We have a logarithm of base 2. It looks like we have a horizontal translation to the right by h. Because of vertical asymptote, h is equal to 1. So y is equal to a times the logarithm of x minus 1 base 2. So if we have the other thing that we've had here, therefore, this vertical stretch, and this is at a height of 2, and it appears to have been vertically stretched now to the height of 6. So that appears to be 3 times as far away from our stretching line. Our stretching line is the x-axis when we have a vertical stretch. And so therefore we can reason that y will equal times 3 times as far away. So y is equal to 3 logarithm of x minus 1 base 2. Now we will get into more algebraic looking at what that is. We'll get to understand how logarithms work in different bases, and numerically how we could solve for that, algebraically how we could solve for that. For right now, just by going from the graph, we can see that it has a vertical stretch factor 3. And so for now, that's all that we're needing to do. All right, so we have a graph here. Here's our partial graph of the logarithmic function of f of x is equal to a log x minus h base b, where b is greater than 1, shown below. So b is greater than 1. That would normally tell us that it should look like this. It should be an increasing function. We see that h has shifted to the right by some amount. So therefore, we know that h is greater than 0. But the fact that this is decreasing tells me what about a? Well, a is a vertical stretch, but it also refers to if we have a vertical reflection. And the fact that this graph is transformed to this shows us that we've had a vertical reflection. So therefore, h is greater than 0, but a has got to be less than 0. And we're almost done here. The graph of each logarithmic function listed below, where b is greater than 1, has a vertical asymptote. So b is greater than 1, so it starts off as an increasing function. The number of functions listed that have an asymptote of x equals 0, so therefore our asymptote should be the y-axis. So y-axis, vertical stretch, the asymptote doesn't change. If we have a vertical translation, it doesn't change. But if we're looking at these last two are horizontal components. And so this is where we're going to have a vertical asymptote changing. This last one, logarithm of x plus 2, this has been a horizontal translation, left by 2. So the vertical asymptote will change. And then this last one, or y is equal to logarithm of 2x. So this is a horizontal stretch factor of a half. And if we think about what's happening with that, if we have this function, if I stretch it horizontally, does the asymptote change? It doesn't, because everything, all of our coordinates on our graph are going to have x values that are multiplied by 1/2. And so everything is going to be closer to the stretching line, which in this case is the y-axis. Because your asymptote is the y-axis, that hasn't moved its asymptote. So the number of functions listed that have an asymptote of x equals 0 is 4, and the only one that doesn't is that last one. Last question, students sketch graphs of y is equal to logarithm of x plus 3 base a minus 7, and g is equal to a to the x minus 2 plus 5, where a, so our base, is greater than 1 in both cases. Graphing these on a coordinate plane, she drew the asymptotes of the two graphs using dotted lines. So Question 6 asks for the intersection of the two dotted lines will be at where. So this essentially is just determine where do we have asymptotes. So we have for f of x, we have a vertical asymptote. Remember that the only thing that's going to affect the vertical asymptote is if we have had a horizontal translation to the left, by 3. So our vertical asymptote, because we've had that as a transformation, is x equals -3. For g of x, it is an exponential. And so therefore it has a horizontal asymptote, and we have a horizontal asymptote that has been shifted. We've had a vertical translation up by 5. And so therefore my vertical asymptote is y is equal to 5. So therefore we put that all together. Where do those asymptotes intersect each other? At -3. All right, well, thanks very much. And again, if you have any questions, please feel free to ask. And we'll see you in the next one.